if you remember last time, I will just remind you briefly, we talked about the binomial distribution, and the idea of probability distributions is, if you're like me and you don't know how to count or just hate thinking about sample spaces and complex probability riddles, probability distributions are for you, because they are a way to say, hey, look, I'm not going to worry about counting. I'm going to look at the problem at hand and try to model it with a formula. Right? So probability distributions, they model probability events. They model random events. They model random processes. All right? And so if you obey the rules, if the probability distribution, each one of those distributions is kind of prepackaged, and it needs to obey some, you need to obey some rules to be able to apply that probability to model the situation at hand. But they give you a way out of having to kind of think about counting, etc. And the best part is that they apply to more complex situations where you might have multiple random variables playing with each other. We'll cover that later with joint probability distributions, etc. So they're a very powerful concept. They take the concept of counting into just doing it with a formula and eventually doing it with calculus. Okay? So we looked at the binomial distribution as our first probability distribution. We said it had some rules to apply to the events have to be, let me go back. What am I doing here? Okay. So we're going to go through the rules of the binomial. The experiment consists of a fixed number of identical trials. So if you're flipping a coin or tossing a die, etc., each trial is independent of the others. There's only two possible outcomes for each trial. And every trial has a probability of getting success called P. Failure is 1 minus P. So you can call success whatever you want. You can call heads success or tails success. It doesn't matter as long as you get your probabilities in the formula correctly. And then the variable you're tracking counts the number of successes in those trials. Okay? And we went ahead and plotted the binomial distribution together. So I'll pull up the plot. I think this is the one of the ones we worked with, I think. Let me move to Creston. Okay, and if you remember, I said that on the y-axis, we're looking at actual probabilities of the actual probability of the event on the x-axis occurring. So we started with a binomial distribution of flipping a fair coin, and there was a chance of getting 50-50 chance of getting heads or tail. Then on the x-axis, you're asking, okay, what is the probability? So this is a distribution with 100 trials. So I'm flipping the coin 100 times. And the x-axis is counting the numbers of possible successes in 100 flips. Okay? So let's say if I pick 42 over here on the x-axis, this vertical bar tells me the probability of getting 42 successes, heads, let's say, 42 heads, in 100 flips of the coin, and that probability is about 0.02 probability, so like just 2% probability of getting that, okay? And then as you get into, higher number, that is going to drop in this case because, you're less likely to get 72 successes with a 50-50 chance. Most of the probabilities are going to be clustered in the middle because it's a fair coin. And then before we left last time, I asked you what would happen if the probability of success is smaller or larger. What happens to that curve? And we experimented with that. Let's say if the probability of success now is only 10%, so you change that P in the formula for the binomial distribution, then you get the following. You have less successes in those trials. So with a 10% chance of success, with 100 tries, you're not going to get a lot of successes. Most of the successes are going to be clustered up to like 18 heads or 18 tails, 0.1 corresponds to. And so you don't have a lot of successes in those 100 trials because the probability of success per trial is very low. And that makes sense. So that moves the graph, makes it asymmetrical, moves the distribution to the left, but it is right skewed, right? So it kind of has a tail to the right. And then with a success of 0.5, of 0.9, well, actually, it doesn't have a tail because we don't have outliers over here. Just moves the entire distribution. It changes the mean, essentially, for the distribution. But we'll get to that later. So the opposite thing happens with a higher likelihood of success. With a 90% chance of success per trial, you're going to carry out a lot of successes in 100 trials. So again, the x-axis is counting the number of successes. You have much more chance of getting 97 or 90, 87, 90, 93 successes in those 100 trials. Okay? So binomial distribution, very, very useful. Let's do some examples. And if you remember the way we did it here in Google Sheets, we kind of plotted the whole thing. If you remember, we put binom distribution, and we applied it to the x value. We gave it the number of trials, and we gave it the probability of success. And then that last entry, we put it 0 for now before we talk about cumulative distribution. Okay? So you can use your Google Sheets to answer these questions, or your calculator if it has binom distribution, or computed by hand, put in the formula by hand. Any one of those works for me. I don't mind. And so after plotting it, we can, this is the same plot I showed earlier. All right, let's do a couple of examples. What's the probability of getting exactly 6 heads in 10 coin tosses? So we already established that coin tosses are a binomial distribution. In fact, that's how the binomial distribution was created. Each coin toss is independent of the other. Each coin toss has only 2 outcomes, heads or tail, success or failure, whichever you want to call success. And we have the probability of each one occurring. This is if we're going to assume a fair coin, so 50-50 chance. So the way you would do this is, I'm missing one thing here. Okay. Now, before we proceed, we also designate, so instead of using just P of x equal whatever, 3 or 4, etc., there's a better nomenclature for these distributions. And we started with the binomial. We're going to call it B for binomial, lowercase b, for a reason. And that looks like B parentheses x. You have semicolon and then NP. N is the number of trials, and P is the probability of success. Okay? So when I say B3, 15, 0.1, that tells you you're getting the probability. What's the probability of 3 successes in 15 trials with a probability of success of 0.1. Okay, that's the nomenclature we will use. So in this case, we know that this is a binomial distribution, and the probability of getting exactly 6 successes in 10 trials with a probability of success 0.5, this is the formula you need to write. So if you go on Google Sheets, I'll show you. If you go on Google Sheets, let me create a new sheet here. Let's create a new sheet. And I can simply put this is equal to binom distribution. And I'm going to give it number of successes is 6, number of trials 10, and probability of success is 0.5. And this is not cumulative, so I put false or 0 at the end. And that gives me 20.5%. Okay? That's the answer. You could put this in your calculator, or you could verify this with the formula for the binomial distribution. Either way works. I'm not going to go back to Google Sheets every time. I'm just going to, now when you see this, you immediately can tell, oh, this is a binomial distribution with 10 trials and probability of success of 50%. All right. Another example, these become fairly mundane. A quality control expert at a large factory estimates that 10% of all batteries produced are defective. If he takes a random sample of 15 batteries, what is the probability that exactly 2 are defective? Okay? So first we need to check if we can apply the binomial distribution to model this. Sometimes it's okay to approximate the situation with a binomial distribution. Go ahead.
How do we know the binomial distribution?
Pardon me?
How do we define binomial probability distribution? How do we know?
The rules? Yeah, so look at the rules. You have to, each trial has to have 1 of 2 outcomes. The trials need to be independent, and you're only doing n trials. Okay, n trials. All right? So now we're getting out of that coin flipping example. Okay, so what do you think here? Let's go through this. So since the batteries are randomly sampled, and presumably more batteries continue to be produced by the factory, while the sampling takes place, we can think of the selection of the batteries to be identical independent trials. So the trial here is picking a battery from the assembly line, up to 15 batteries. So that's our experiment. This is like tossing a coin. We're going to pick a battery. Now, what are the two outcomes? Functioning, defective, right? Those are our two outcomes. All right. Now, they give us, so our trials, we have 15 trials because we're picking 15 batteries. There's two outcomes, either defective or not. Okay. Now, they gave us the probability that a battery is defective as 10%. So we can use defective as our success. Say if the battery, the success rate is 10%, okay, we can count then the number of successes. That success means battery is has failed. Doesn't matter. Success doesn't mean, in this sense, success means that you chose the thing you're looking for. Okay? Or you can flip it around. You can say the battery is not defective and the probability is 90%. Both will give you exactly the same answer. Okay? In fact, we should try this. All right? So the answer here is, what is the probability of getting 2 batteries to be defective with 15 trials and a probability of 10% of success? So in other words, getting 2 defective batteries, picking 15 batteries with a probability of being defective equal 10%. This is equal to 26.7%. And this is identical. So let me show you what this should be. This will be identical to B2, so B 13, 15, and 0.9. So this would be identical to this. So this will be identical to this, right? Because here our measure of success is that 13 non-defective batteries. And the probability of a battery not defective is 90%. Okay? So this would be the same, this would give you exactly the same result. Okay? Because the binomial is a symmetric distribution, right? I said asymmetric earlier, thinking of the whole thing as a tail, but if you really discretely, it is fully symmetric. So on either side of the middle, the probabilities are going to be identical. Okay, now I'm going to change the question a little bit here. Same guy, same dude, a quality control expert in the factory, 10% of batteries are defective. Now he takes a random sample of 15 batteries. Now we're asking what's the probability that no more than 2 batteries are defective. Okay, no more, we are only allowing 2 batteries at most to be defective. Okay? So how do we answer this question? So we want, yes?
Can we just have the probability of everything below 2 then?
Everything below 2, including 2, right? Yep. So your colleague is saying that this is equivalent to saying, what is the probability of getting 0 defective battery plus a probability of getting exactly 1 defective battery plus getting exactly 2 defective batteries? What is that probability, adding them all up together? Okay, in other words, we're looking for the probability that x is less than or equal to 2. Not exactly 2, less than or equal to 2, because you could pick 0 defective, 1 defective, or 2 defectives. Okay, so, but no more than 2. Okay? So the way to do this is you simply write it as probability of x being less than or equal to 2, and that's exactly equal to the probability of x equals 0 plus the probability of x equal 1 plus the probability of x equal 2. Each one of those is a binomial distribution. So this would be B0, whatever, and then this be B1 at trials and probability of success plus B2, et cetera, et cetera. You add them up and you get a number. Okay? Now, when you look at this in a distribution, so this is the setup for the problem at the plant. Okay? At the this is the setup for the problem that this guy is working with, and this is the binomial. We have 15 trials, all right, with a probability of success of 0.1 for finding a defective battery. So this is the distribution. And 0 successes, 1 success, 0 defective batteries, 1 defective, 2 defectives, and so on, all right? what we're asking is, what is the sum of these 3 bars? What is the probability of getting no more than 2 defectives? In other words, what is the sum of these 3 bars over here? And we can highlight it like this, okay? So this would be the probability of getting exactly no more than 2 defective batteries, okay? Now, we did this before. Remember when we were looking at descriptive statistics and we asked what is the cumulative salary? And we said, oh, no more than 6 people are making $80,000, right? This is exactly what we're doing here. We're just summing up the frequencies for each occurrence on the random variable. So this actually has a name. It's called a cumulative mass function. And is defined as, it represents the probability of x being less than or equal inclusive of some value. So the probability of x less than 3, less than or equal to 3, that is called the cumulative probability at x equals 3. So we call this the CMF. Okay, so the cumulative mass function represents the probability that P of the random variable is less than or equal to a certain x value for a PMF. PMF is the probability mass function. Be very careful with those. We're going to change the nomenclature when we go to continuous. And it's defined as the sum or accumulation of all probabilities preceding and including x. So the way we write this is CMF of x instead of PMF. We call it CMF of x. That's equal to the sum of all your probabilities up to and including the x value. Okay? So in other words, for our problem, we could have called this is the binomial CMF at 2. Okay? And it would automatically add them up. Now, this is actually a function that you can just use in Excel or Google Sheets. You remember that last argument we had for the for when we were plotting the binomial, if you want the cumulative or not. So you can use that and you get the cumulative distribution. You don't have to add it manually by hand. And we'll do this in a second. Okay. Now, later we will see CDF, or a cumulative density function, which represents the same thing but for a probability density function. Now, those will have different meanings and different implications mathematically. I just wanted to introduce it here. We'll get back to it once we get on Thursday. Okay. The same way we called the binomial distribution, gave it a symbol, lowercase b, we will give a symbol to the cumulative distribution and call it capital B. So now when you see the lowercase b, you know that this is probability mass function of the binomial distribution. And when you see a capital B, you know that this is the cumulative mass function of the binomial distribution. The cumulative gives you the probability that x, the variable, is less than or equal to this x value that you have in the capital B. Okay? And you can actually plot this cumulative mass function. It adds the probability. So this is one of the binomial distributions. And so the CMF at 0 gives you, that's the first probability. The CMF at 1 is equal to the probability at 0 plus the probability at 1. The CMF at 2 gives you the probability at 0, 1, and 2, and so on. Now you notice eventually at the last trial, your total probabilities are going to be what? 1. Your CMF is going to be exactly equal to 1. Why? Because all probabilities need to add up to exactly 1. You might reach 1 earlier, and that's fine, but nothing else can be higher after that. Okay? It means you've accomplished, all of the events have occurred at whatever value occurred earlier. Okay? So let's go back to this, to the guy with the batteries. All right? So we have a binomial. We'll do another one here. We'll do a binomial distribution. All right? So this time we want the cumulative mass function, the CMF, of no more than 2 batteries being defective. So our x value is still 2. So this is capital B at 2. And we have what? 15 trials, right? 15 batteries. The probability of success is 0.1. And now cumulative, we want it to be 1. We want the cumulative, okay? And if you close this, then gives you, there's a 40% chance of finding no more than 2 defective batteries. Okay, so no more than so you could have 0, 1, or 2 defective batteries at most. There's a 40% chance of seeing that. All right, so the CMF is super useful because we're gonna start thinking in terms of intervals as we go to continuous probabilities. Intervals are going to be very important. So the CMF allows us to do that. So let's work some examples on the math for CMFs. This is the binomial distribution with 15 trials and a probability of 50% for success. So you see it's in a nice and symmetrical, and it goes up and then goes down, 15 trials, okay? And for example, all of these columns up to here, all of these guys, there's almost 0 here, there's a very small value here if you don't see it. But all of these guys, together, they represent the cumulative mass function B at 5. Agreed? So visually, when you're calling the cumulative mass function at 5, you're adding all the probabilities up to and including 5. Okay, so let me ask you now this. What is this guy? I'm adding all the way from 0, 1, 2, all the way to 8. This is capital B at no? So this would be measuring the probability of getting no more than 8 successes. So this would be B at 8, capital B at 8. It's summing up all of these together to get you the cumulative probability to get no more than 8 successes. Okay? These are the questions that you will see on exams. Okay? All right, what is this? Remember that the total probabilities are 1, sum up to 1. Okay? Yes? Well, I'm not asking about what it means, but sure, we can think about it like what is the probability of getting more than 10 defective batteries, right? But what is the math? How do I express that with math using the capital B? So we agree, Ashton.
Like, could we just have it as like a -5 of counting back, or
Almost.
Maybe doing it up to 9 and then 1 minus whatever you got.
Okay. Okay. So that's the right answer. All right. So all of these guys, all of them, they're B, capital B at 9. Agreed? That's the probability of no more than 9 successes. Okay? All of those, if you add them up together, that will give you B at 9. But we want this. Okay, so if this is B at 9, what is all of it from end to end? It's 1, because all the probabilities add up to 1. So if we do 1 minus B at 9, it's going to give us this. Right? Okay, that's using the complement rule. Right? If you do a Venn diagram, this is giving you the complement. Okay, what is this? What is the probability of having, now this is going to be, of having no less than 6 defective batteries, but no more than 10? These are legitimate questions that you will ask in a statistical analysis. How do you get that from the CMF? You could go and say, I'm going to add B, lowercase b, binomial at 6 plus binomial at 7. What if I had 2,000 of these? That's silly to do. So, yeah.
You do the distribution of more than 10.
Okay, so what is the value? Capital B at 10. Okay, so capital B at 10 gives you all of this. Agreed?
Yeah,
Minus B at 5. That's right. Okay, so to get these guys, you're doing B at 10, cumulative at 10, gives you all of this, minus cumulative at 5, and then you're going to get this. Okay? That's it. And this is exactly how you do it in Excel or in your sheets. Okay. All right, so let's get this to work. What is the probability that a salesperson gets a sale more than 2 times in 6 sales calls if the probability that the salesperson gets a sale on any given call is 50%? So we have this guy who's got a 50-50 chance on landing a sale at any given call. Okay, now we're asking if he gets 6 calls in today, if he gets 6 calls, what's the probability that he gets a sale more than 2 times? So more than 2 sales in those 6 sales calls. Okay, so this is first you check, is this a binomial? Yeah, the sales calls are independent of each other. As far as I know, you have these call centers, random calls come in. It's not like one person, it's very rare. You know, you call the guy and then you tell your friend to call, and that it's rare that that happens. It's just usually random calls. And there's 2 outcomes per call. One of 2 outcomes, either a sale or not a sale, right? So the trial has 2 outcomes. We'll call a sale success. The probability of success is 50. So this is a binomial distribution. And we're looking for the event that X is greater than 2 now. Greater than 2. More than 2 sales. So we want 3, 4, 5, and 6 sales. That's the total number of sales we can get, right? Because it's got 6 calls. So the probability that X is greater than 2, in this case, is 1 minus the probability of X less than or equal to 2. That's what we showed with the complement, right? And then the probability of X less than or equal to 2 is the cumulative at 2 exactly, right? So you get 1 minus cumulative at 2, and you get the answer, 65% chance of landing more than 2 sales in the next 6 calls. Okay, so it will look like this, right? If I were you, I always like to plot them. I'll get the binomial, I plot it, I look at it, I visualize it, and I'm looking at 3, 4, 5, and 6 sales. So I'm looking at this. So this would be 1, all the probabilities minus the cumulative until 2. Okay. All right, on to the next distribution. We'll go a little faster here. The next one is called the hypergeometric distribution. Now, we start with a binomial because the binomial shares a lot of commonalities with all the distributions that we're going to learn. This next one, the hypergeometric distribution, is identical to the binomial except that trials are not independent, or in other words, trials are dependent on each other. In other words, you're doing sampling without replacement. Okay? You're taking, you have some trick doing when you're flipping the coin where, you know, the next subsequent trial is dependent on the previous one. And so this is the only difference between everything else occurs. You have n trials, a fixed number of trials, and you have 2 outcomes per trial, success or failure, but the trials are dependent on each other. Okay? So that's the difference. And the rules is that, again, each trials consists of selecting one of the n items in the population, and the experiment consists of n trials, the total number of possible successes. Oh no, hold on, this is wrong. This is for the, actually, hold on, yes, never mind. I thought this was, yeah. Okay, so we have a population with n items in it, so like, you know, the grocery aisle with, you know, 200 boxes of cereal, right? Or whatever, you know, the battery plant with 2,000 batteries. Okay, that's the total number of items in the population. And then you're doing, you're sampling from that total population. You have the capital N for the population, lowercase n for the number of trials in your sample. And the total number of possible successes in the entire population is K. So you need to know in your total battery power plant, how many batteries in general are not defective or defective. All right, so you have 1,000 batteries, maybe 20%, 10 of them or 100 of them are defective. Okay, so you know that information. The trials are dependent on each other. So in other words, you're sampling, but you don't put the battery back. You take the battery out, you take the battery out, you take the battery out, and test it. Okay, you don't replace them back. The hypergeometric random variable counts the number of successes in those n trials. So it looks exactly the same as the binomial distribution. On the x-axis, you're counting the number of successes. So how many, 6, 7, 10 successes, etc. And they're giving you the mean value and the variance. So these are, it's nice to have a distribution because you get a formula for the mean and the variance. So use those formulas when you're computing them for distributions. Don't use the ones in Excel because it might give you a sample variance rather than a population variance. Okay, now the formula for the hypergeometric distribution, we're going to call this lowercase h because capital H is going to be referring to the cumulative hypergeometric function. And the hypergeometric mass function has your standard x parameter, that's your random variable, what value it takes. But now you have three parameters, n, lowercase n, k, and capital N. So lowercase n is how many trials you're running. You're sampling 15 batteries out of 1,000. K is how many successes in the population. So there's no more concept of probability of success or failure. Just successes, number of successes in the population. And capital N is the population size. So it's a nasty formula. It has the product of, not very nasty, but it's kind of computationally can get a little bit overwhelming. So it's got combinations in the numerator and in the denominator, okay? And make sure you don't confuse the symbols, lowercase n, capital N, x, and k, etc., okay? Now, thankfully, there's a built-in formula for that in Google Sheets and Excel, etc. And now there's limitations on this formula. And when I was trying to plot it to show you how it looks like, you'll always get in trouble for what values you can plot over. So you can't just plot from x equals 0 to x equal number of trials. No, there's limitations on the minimum value of x and the maximum value of x. You can look that this distribution is valid. And those are primarily driven by the subscripts on the combinations formula. So if you look at the first one, x must be less than k, but also x must be less than n, lowercase n. So in other words, the maximum x that can occur is going to be the smaller of these two values. Okay, that's your maximum x that you can achieve, or the maximum number of successes in a given experiment. Now, on the other hand, if you look at that other formula, n minus x must be less than n minus k. Otherwise, you can't do the combination, okay? So at most, those would be equal, but this one must be less than that one. And x must be positive as well. And so if you run the math here, you'll get that the minimum value of x is either 0 or n minus capital N minus k. So, you know, it's unlike the binomial distribution where you plot from 0 successes to exactly 15 or whatever n trials. Here, you can't. Even if you have 20 trials, your x min could be 5 and your x max could be 10, because it depends on the size of your population and the k value that you have, okay? You can try it and get in trouble with that. All right, so let's start with an example. At the local grocery store, there are 20 boxes of cereal on one shelf, half of which contain a prize. Ooh. My kids are suckers for like these things. Like, oh, look, it's got like a toy in it. You have to collect like 2,000 boxes and then call the president to, you know, send in by carrier pigeon. It's like, what's the point? I have like a pile of boxes. Like, I'm not going, but Dad, we want to collect those. It's like, just here's $5 and go away. Anyway, so suppose that so our population is 20 boxes of cereal. Okay, that's our population. Agreed? Now, half of them contain a prize. So our capital N is 20. Half of them contain a prize. That's K. So 10 of those boxes contain a prize. So that's the amount of successes. Success means containing a prize. Okay. Now you go and pick 3 boxes of cereal without replacement, because you're taking them home. Last time I tried, Smith would not accept an empty box of cereal as a return because they told me you already ate it. I was like, but it didn't taste good, but they said you ate it, so it must have tasted good. So anyway, so there's no replacement. You're taking the box home, okay? And you're either throwing it away or keeping it. So no replacement. Trials are not dependent on each other. You take the first box, you reduce the population now, right? From 20 to 19, you took the second box, now 18. You took the third box, now 17. What's the probability that all 3 boxes contain a prize? Okay, So what's the probability that we have 3 successes? Exactly 3 successes. Not at least, not at most, yeah, exactly 3 successes. Okay, so we can check that this is a hypergeometric distribution. We have an outcome, success or failure. Trials are dependent on each other because you're not doing replacement, etc. So you run this and this is the formula you need, a hypergeometric distribution exactly at 3. And your trials are, you have 3 trials and you got 10 successes and 20 items in the population. So you can do this in Google Sheets. Okay, so let me see what I got here. Okay, oh, all right. Oh, come on, Google Sheets. So let me see what I got here. Okay, what the heck? Let's just do a clean one. We'll do a equal hypergeom distribution. So you'll always see hypergeom dist or hypergeom dot dist. They're the same. Just pick the first one. Now it tells you number of successes, number of draws, and successes in population, and the population size. Okay. Now, for some weird reason, they don't have a cumulative option for the hypergeometric distribution in Google Sheets, which was so weird. Like all the other Sheets software, they have it, except Google Sheet. I don't know. So anyway, number of successes, we're looking for exactly 3 serial boxes. The number of draws, all right, so the number of draws is going to be 3. We're picking 3 boxes out, right? That's 3. The number of successes in the population is 10 because we know that 50% of the 20 boxes have a prize in them. So 10 of them have prizes. And the total population size is 20. And if you execute this, you get 10.5%. Okay? You get 10.5%. Right? Exactly what I have here. So if you plot it, it looks like this. But this one is going to range from 0 to 3 because at most you're picking 3 boxes. In this case, it goes from 0 to 3. Okay. There are 7 yellow and 9 green marbles in a bag. Okay. So we have a bag with 16 marbles. 9 of them are green. 7 of them are yellow. And if 5 marbles are chosen at random without replacement, so the trials are dependent. Okay. No replacement. What is the probability that exactly 3 of the marbles chosen will be yellow? Okay, so exactly 3, you know that you're picking the distribution. It's not cumulative. You're picking one value for the probability. Okay, exactly 3 will be yellow. All right, so first thing you figure out, okay, this looks like a hypergeometric. It is a hypergeometric. Checks all the marks. Total population is 7 yellow plus 9 green marbles. That's 16 total population. The number of trials is 5 because we picked 5 marbles. Our x value for the random variable is 3. And we are left next is to determine the number of successes in the population. Okay, so how many, we're going to call yellow to be a success because that's the question. How many marbles will be yellow? What's the number of yellow in the population? It's 7. So k is equal to 7. So if you run this, you get k yellow, x equals 3, number of trials is 5, total population is 16, and you just plug it into the hypergeometric formula, get a number. I don't know if your calculators have those. You're welcome to use that on your calculators as well, and just simplifies things a lot. Okay. Okay, pretend that this is not here, okay? Because I forgot to put in animation for it. So pretend that this is not here. I'm going to hide it. Okay. A shipment of 25 light bulbs contains 3 defective bulbs. Okay, so we got a shipment from Amazon has 25 bulbs. We know that 3 of them are defective, okay? And we're going to pick 5 at random without replacement. So we're going to pick first one, second, third, fourth. So without replacement, that means dependent. These trials are dependent. What does a trial mean in this case? Picking a light bulb. We're not replacing it, so the trials are dependent. What's the probability that fewer than 2 of the bulbs chosen are defective? Now, once you hear the word fewer, Okay, fewer, it automatically rings a bell that this is a cumulative mass function. So you need to think about adding the distributions. Now, we're saying fewer than 2. Okay, so this means less than 2 or less than or equal to 1. Agreed? So less than 2, which means less than or equal to 1. Okay? And then we just invoke the cumulative hypergeometric mass function, which we're going to designate with capital H. So capital H at x means the probability that we have exactly less than or equal to this value over here. So what we're looking for is really capital H at 1, because P is x less than 2, fewer than 2 bulbs. So this means exactly 0 or 1 defective bulbs, okay? And then you push the numbers in, and yeah, it just works. Now, if you're doing this in Google Sheets, you don't have a cumulative option. So you have to sum them up by hand, okay, in the sheet, all right? So you have to sum them up one by one. All right. This is getting like mechanistic. We'll do this last one. We'll do this last one with the complement. A produce distributor is carrying 9 boxes of Granny Smith. Who likes Granny Smith apples? No. I like Granny Smith apples. And they're, okay, here's a trick. So you like tarty and like a little bit sour, right? Yeah, so try them with salt. It's a Mediterranean way of eating sour or tarty apples. Try them with a little bit of salt. Like my kids love it. They're like, send us, apples with salt to school. They're like weird at school. Why do you have salt with your apples? Like, it's from different foods. Anyway, but it's good if you like that sour citrusy flavor. Okay. So a distributor carrying 9 boxes of Granny Smith apples and 8 boxes of Golden Delicious apples. Okay. So we have 9 and 8, we have 17 total boxes. 4 boxes are randomly delivered to a local market. Yeah, so it's like, oh yeah, I have boxes of apples, which is gonna randomly give you whatever apples. No, I only need Granny Smith. No, we're just gonna give you any random apples. That's all you get today, sir. Okay, so what is the probability that at least 3 of the boxes contain Golden Delicious apples? So at least 3 of the boxes contain Golden Delicious apples. So now, when you take out a box, you're not putting it back, right? So no replacement. So trials are dependent on each other. Picking a box is one of our trials, and success is going to designate picking a Golden Delicious apple, a box of Golden Delicious apples, okay? Now, what's the probability of getting at least 3 boxes? So that means x greater than or equal to 3. What's the probability that x is greater than or equal to 3? Successes, all right? So you run through the numbers to figure out what the population is. So population, 17 total boxes of apples. We're picking 4 boxes at random, all right? So lowercase n is 4. Number of successes in the number of successes we're looking at is x at least equal 3. So our x is greater than or equal to 3. So we need at least 3 boxes. And total successes in the population, in other words, how many golden delicious apples are in the population? We got 8. So you put this, you're looking for the probability that x greater than or equal to 3. Because the cumulative function doesn't do this, we have to take the complement. So this is 1 minus probability of x less than 3, not inclusive, which means this is 1 minus capital H cumulative mass function for hypergeometric exactly at 2, because this is x less than 3 means x less than or equal to 2. This is in discrete world. And then you get a 24% chance of getting the Golden Delicious apples. Okay, so those who like the Granny Smith, this is good luck for us, okay? All right, now here's a little thing for your knowledge, for your own knowledge. The binomial distribution can serve as an approximation to the hypergeometric distribution, okay? So note the difference, some of the differences between binomial and hypergeometric. In the binomial distribution, we only had trials and a probability of success, okay, as the other parameters. You had n and p. with the hypergeometric, we had n, k, and capital N. Now, k is number of successes in the population, and n is the total population. If you divide k by n, what does it give you? The probability of success in the population. Agreed? Okay. So if you get that, then you ask, when can we use the binomial? Because they look the same. Although the trials are dependent, but is there a limit where we can probably switch to the binomial? Why would we switch to the binomial? It's a little cheaper to compute for large values of n. Well, it turns out that for large values of n, indeed, the hypergeometric distribution becomes equal to the binomial distribution. So the rule of thumb is that if n is large, good rule of thumb is to use binomial distribution, approximately hypergeometric distribution, if n is less than capital N over 10. So if n is large, in general, you can just switch to the binomial distribution, even if the trials are dependent on each other. Okay? So it gives you great segue to say, you know what, I'm just going to try to model this process as a binomial distribution, even if you're making a mistake, even if the trials are dependent on each other. You know, that's the power of using distribution. We're not looking exactly for counting and getting exact probabilities. You know, we're modeling these events. This becomes useful when you're doing more complicated, more complex events modeling. Okay, the one before last distribution we're going to look at is the Poisson distribution. Okay, can you say Poisson? Poisson, Poisson. Poisson, I had a friend in Tennessee, he was like Poisson. So Poisson actually means fish in French, the word Poisson. So the fish, this is the fish distribution. But yeah, it sounds like Poisson, Poisson, Poisson distribution. Okay, so similar to the binomial distribution. Okay, so we started binomial, we had n trials. Trials were independent of each other. When we switched to hypergeometric, the trials were dependent on each other. Okay? Now we're going to go back, trials being independent of each other, but we're not going to have a fixed number of trials. So you see what we're targeting? We're targeting like all three possible options. We have fixed trials. Trials were dependent on each other and independent of each other. That was fixed trials. Trials were dependent on each other. That's hypergeometric. No fixed trials, but trials are independent of each other. That's going to give you the Poisson distribution, the fish distribution, okay? So it serves as a model for counts which do not have a natural upper bound. So you're looking at a period in time. How often is your internet router with Comcast is going to fail in the next hour when you're working at home and have like an interview or something, right? You know, it doesn't happen with Comcast, of course, you know, but it always does, right? So when you ask that, when you ask that question, how likely is it to fail in the next 3 hours? You know, 3 hours is not a trial. You're not doing a trial here. It's a period of time. What's the chance that there's a defect on 20 feet of drywall? Or 15 defects, right? It's not a trial. You're not picking different drywalls. You're taking a length, right? And a length is a continuous period of a continuous space, right? Whether in time or space. So the Poisson distribution does that. Every time you hear, what's the likelihood this thing is going to fail in the next 3 weeks, or there's a failure in the next 2 miles, Poisson distribution. Immediately think Poisson distribution, okay? Okay, so here are the rules. The Poisson distribution is discrete probability for the number of possible successes over a given interval of time and space, all right? Interval of time and space, okay. Each success must be independent of any other successes, okay? Most of the time, they're not, but we assume that they are. The Poisson random variable, x, counts the number of successes in the given interval. Okay, so how many times is your internet going to fail in the next 3 hours? Okay, 15 times, etc., right? So it counts that. The mean number of successes, lambda, in a given interval must remain constant. So in other words, on average, so let's say you installed your internet at home and you know that over the past year, oh gosh, you know your internet failed on average 2 times per hour, okay? Now some hours is gonna fail 10 times, some hours is gonna fail 0 times, but on average, it's been failing 2 times per hour, okay? You take that as your mean number of successes per interval. Now you define that interval. Could be 1 hour, could be 10 hours, whatever. Okay, but as long as you're clear about what that mean, what the mean lambda is. Okay, and then for a Poisson distribution, we have the mean and the variance that are exactly equal to lambda, which is a very interesting result for the Poisson distribution. We'll get to derive those once we go to the continuous versions. And lambda is the mean number of successes. Okay, this is the formula for the Poisson distribution. Very simple. You only have your random variable and only have that mean number of successes per interval, per unit interval, which is really simple. You get lambda to the x, e to the minus lambda over x factorial. If it weren't for the x factorial, this would be a continuous distribution. Okay, but you can approximate the factorial with a continuous Stirling formula, it's called. But okay, we'll see. So let's start with an example. A barber usually finishes one haircut every 15 minutes, okay, on average. All right? So you hear time, 15 minutes, that's going to be a probability question. And we have time is going to be a Poisson distribution. One haircut per 15 minutes, that's my lambda. Okay, that's going to be my lambda. Calculate the probability that our barber is feeling extra speedy one day and finishes 6 haircuts in 1 hour. So now we know that baseline, he does 1 haircut per 15 minutes. Our interval of interest is 1 hour. Okay, so now we've defined our interval. What is that lambda over that 1 hour? We expect to do 4 haircuts per hour on average, right? Because he did 1 haircut per 15 minutes. So on average, we expect 4 haircuts per 1 hour. So that's actually going to be our lambda for the Poisson distribution. Now, that 1 hour, it never shows up in the formula for the Poisson distribution because it is embedded in the lambda. Okay, so that's what's really important for you here to recognize is that although you're given 1 haircut per 15 minutes, your interval of interest is 1 hour. So you need the lambda for that 1 hour. And that lambda is 4 haircuts per hour. All right? So you take that lambda, you plug it into the formula for the Poisson distribution, and what is your x is getting 6 haircuts in 1 hour. So probability that that x is exactly equal to 6 is about 10.4%. And you can do this with your Google Sheets, and you can say this is equal to Poisson. Okay, Poisson.dist or Poisson. And you're looking at x equals 6. What is the mean? It never asks for the length of the interval because that doesn't matter to the Poisson formula, because that's all embedded in that mean value lambda. So we have 4 haircuts per hour, and this is not cumulative, so gives you 10.42%. Okay? All right. For health reasons, homes in Utah need to be inspected for radon gas, which decays and produces alpha particles. So I told you in numerical methods that I have a radon tracker at home, a continuous radon monitor. So I measure alpha particles, continuously every 6 minutes, and I have data like for an entire year. Unfortunately, it deletes them, so I have at the end of each year, I have like on my calendar, go save the radon data because I want to have like 15 years worth of data at our home for some weird reason. But anyway, so one device counts the number of alpha particles that hit its detector. Okay, so those could cause cancer. They're radioactive. Utah has the lowest rate of smokers, yet one of the highest rates of lung cancer because of radon. Nice. I mean, like it's a scary statistic, but because of the granite in our soil, and the closer you live to granite, so we live in Sandy, closer to the granite town, with the little cottonwood over there. There's a lot of granite in the ground, so that produces a lot of radon gas. Comes through your basement. When the weather changes outside, you have high pressure, low pressure, pushes it out. There's cracks in your basement. If you're renting a basement, keep a couple windows open, even if it's cold. If you don't have a radon mitigation system, if you're renting a basement, all right, either do a measurement or just open up a couple of windows just to keep, it's a gas, it flows, you can just take it out, doesn't matter, put a fan and push it out of your space, okay? Now, to a good approximation, the count for the next week follows a Poisson distribution with a mean of 1.3. So we know that now our interval is 1 week, and we have lambda is 1.3 particles per that week. So now the probability, find the probability of exactly 1 particle next week, the probability of 1 or more particles next week, so x greater than or equal to 1, and the probability of at least 2, but no more than 4 particles next week. So covering the entire gamut of cumulative stuff. All right, so the probability of exactly 1 particle next week is f x equal 1 and lambda equal 1.3, and you get that value. Probability of 1 or more particles next week. So 1 or more particles, so that's x greater than or equal to 1, right? So that's P of x greater than equal to 1. Now remember, the cumulative only does x less than or equal to something. So we need the complement. So this would be the complement of P of less than 1 strictly. So that's cumulative exactly at 0, right? So that's 1 minus f at 0, and you get about 72%, 73% chance of getting 1 or more particles next week, okay? Next week. And then finally, at least 2 particles, but no more than 4 particles. So that's x between, inclusive, between 2 and 4, okay? So that's P of x, 2 and 4. And so that gets you into the cumulative at 4 minus the cumulative at 1. Remember, because 2 must be included in the calculation. So you're counting probability at 2, probability at 3, plus probability at 4, okay? So you're counting all 3, and there's a 36% chance you end up in that situation. Okay, now on to the internet problem and dial-up. Like, who does dial-up these days? I don't know why I put this example. Okay, does anybody have dial-up? I remember like when dial-up came to, and like my brother would be on the phone, get off the internet. I'm like, you get off talking, to your friends and whatever. My brother was older. He was like, going out a lot at the time. I was just a little nerd sitting in a little corner in the kitchen, trying to connect to the internet. So, okay, so suppose that the dial-up internet connection at your house goes out an average of 0.9 times every hour. So almost 1 time per hour. If you plan to be connected to the internet for 3 hours one afternoon, what is the probability that you stay connected the entire time? So we're looking exactly for the probability at x exactly equal 3. Our interval is 3 hours. So we need the lambda for those 3 hours. Now we know it fails 0.9 times every hour on average. So we need to multiply that by 3 to get the lambda for our interval of interest. Agreed? So our lambda is 3 times 0.9, which is 2.7 times in those 3 hours. And you just plug that in. So f, what is the probability that you stay connected exactly? So no failure, okay? No failure. So 0, f at 0 with lambda 2.7 is very low, like 6-7%. So it's a you're gonna drop the connection. Okay, let's do this one again. A math professor averages grading 20 exams per hour. Geez, like using darts, to grade. Okay, what is the probability? Was that an episode in The Simpsons, I think, or something? Yeah, there was like grading with like, okay, exam 1, what's the grade? Okay, we don't do that. So what is the probability that the grade, okay. So what is the probability that he grades more than 35 of his 60 statistics exam during an uninterrupted hour and a half between classes? Okay, so our interval is 1.5 hours. He does 20 exams per hour, so multiply that by 1.5, you get 30 exams. That's your lambda. On average, he will grade 30 exams in that interval of 1.5 hours. Okay. And then what's the probability that he grades? He grades more than 35 of his 60 statistics exams. So x greater than 35, right? So f of x greater than 35 is 1 minus f of x less than or equal to 35, which is cumulative at 35, right? So you got about 60% chance of accomplishing that. All right. One more piece for your knowledge is that the Poisson distribution is an approximation to the binomial distribution. So the binomial was an approximation to the hypergeometric. The Poisson is a good approximation to the binomial distribution. So it approximates them all and is the cheapest to evaluate. When you take a binomial, when the number of trials approaches infinity and when the probability approaches 0, then you can use the Poisson distribution. What we call this is that this is the probability of rare events. As p approaches 0, this is a very rare event. N approaches infinity, a lot of things going on. So you have a lot of trials, very small. The product, as n approaches infinity and p approaches 0, n times p is a finite number. So there is a chance that even an event that's a black swan, that's a very rare event to happen, that it will happen. Okay, and the Poisson distribution will model that very beautifully. Okay, I'm gonna skip the multinomial distribution. We might come back to it later, but the multinomial distribution extends the binomial distribution to when you have more than 2 outcomes. Okay, let's say with die we have 6 outcomes, or you have your ranking professors. Mediocre, good, very good, excellent, right? So you have multiple outcomes per trial, and you want to track all of those, and you will have a probability for each one. So I'll share the slides. You can look at it. It's not even in your textbook, so I added that from another textbook, but I thought it was useful. Okay, this is what's important here, is determining which probability distribution to use. So if you look at this table, looking at binomial, Poisson, and geometric in the columns, and in the rows, of course, they're all discrete distributions. What are the conditions? Independent trials or fixed number of trials? So binomial, both independent and fixed number of trials. Poisson, independent trials, but a length of time. There's no fixed number of trials. Could be 50 trials, 1,000, doesn't matter. It could be an infinite number of trials. Hypergeometric, trials are dependent, but it's still a fixed number of trials. Okay? I'll go through 3 examples, one for each. Okay? So based on data from an online search provider, a new company believes that its website is viewed 1,500 times a week. Okay? What is the probability that in the next 4 weeks, the company's website will be viewed more than 5,000 times? What can model this? The second you hear period of time, weeks, like immediately Poisson. Now, viewing the website is the trial. Agreed? And they're independent. I'm in Sandy, you're in San Diego, whatever. Viewing the website, we're independent. Okay? So the trials are independent. It is a Poisson distribution. Okay. Assume that the proportions of in-state and out-of-state applicants to the U of U has remained constant for the last several years. Okay? So I said years, but it doesn't mean Poisson yet. And that 58% of applicants are in-state and 42% are out of state. What is the probability that the next 250 applicants, no more than 100 of them are in state? Okay? So I have a fixed number of trials, 250 applicants, right? So that rules out the Poisson equation, right? Because Poisson equation doesn't have a fixed number of trials. So we're debating which one of those. Now, picking a student, whether they're in state or out of state, okay, that's independent. When an applicant applies to the university, an out of state applicant is not connected to someone applying at the U from Utah or not, right? So this is a binomial distribution, okay? And finally, this is going to be hypergeometric, obviously, like by elimination, okay? Of the 500 programs printed for the university opera, okay, we don't have a university opera, so this is not an example from the U. Several contain coupons for the local coffee shop. Of these coupons, 100 are $1 off coupons. Wow, That's amazing. $1 off a $10 coffee cup. That's really gonna make a difference. And 50 are for a free latte. Now I could go for a free latte. That's a good one. Okay, assuming that the different coupons are randomly distributed throughout the programs, what is the probability that the first 50 programs that are handed out each contain a coupon for the coffee shop? So we have a fixed number of trials, right? So we're randomly distributing coupons, and we have 50, the first 50 coupons that we're picking. Now, when you pick a coupon, you don't put it back. When you pick a pamphlet, you're not putting it back. So each subsequent brochure you're giving is dependent on the previous one, right? Because there's no replacement. So this gets you into a hypergeometric distribution, okay? Okay, if you'll allow me, I have like, what, 10, 12 minutes left. I want to go over the last question I asked you in the quiz, okay? And by the way, we're done with discrete distributions. That's it. On Thursday, we'll start with continuous distributions.